Okay, so now we're going to look at situations, certain molecules and polyatomic ions, where the octet rule is not followed. So if you recall, when we were learning about drawing the Lewis structure of molecules and ions, we tried to make sure that the number of electrons on each atom is 8, excepting, of course, for hydrogen, which would be 2. But this is not possible in all cases, and we're going to see some examples of this right now. Excuse me. So, a few comments here before we get into the actual examples. There are certain molecules, for example, that would have an odd number of valence electrons, and therefore that means that at least one of them would be unpaired, and therefore we call these free radicals. So obviously, if a molecule will have an odd number of valence electrons, obviously it won't have 8 electrons on its valence shell, because after all, 8 is an even number, all right? There are other situations where molecules will have incomplete octets, right? And these are usually compounds of beryllium, boron, and aluminum, right? And as a result, they have some very unusual characteristics in terms of their bonding structure, and they're also very reactive, all right? And the main reason why they're very reactive is because they have an incomplete octet, and they will try to, in their reactions, gain enough electrons in order to complete their octets, all right? Also, you have some compounds that have what we call expanded valence shells. In other words, these compounds will have a central atom that can have more than 8 electrons around it, all right? So in these cases, you will have situations where instead of 8 electrons, you can actually have more than 8 electrons on the central atom. Now, and we're going to see some examples of that shortly. In fact, before we see that, very important comment right here, and that is that a central atom can have more than 8 electrons if it is in the 3rd period or lower, all right? So basically, the only atoms that can have more than 8 electrons on its outer shell are those atoms that would belong to period 3 and all the periods below period 3, 3, 4, 5, all right? Elements in periods 1 and 2 simply cannot have an expanded valence. And the reason for that I won't get into now, but that will be covered in the next chapter, all right? So that's something that you can look forward to. So that will be covered in chapter 10, all right? So these are some things that you have to consider when it comes to molecules where the atoms do not follow the octet rule. So the best way to demonstrate this is to go straight into some examples. And we have this question here, which gives you some formulas, and they're asking for you to determine the Lewis structures. All right, so the first one I'm going to deal with is BrF5, bromine pentafluoride. So let me clean this up here. So let's look at BrF5. So we go through the steps as we did before. Bromine will contribute 7 electrons, and each fluorine will contribute 7, but we have to multiply that by 5, so that gives you 35 electrons. So when you add this up, this gives you a grand total of 42 electrons, which will be equal to 21 pairs, all right? So we put the bromine in the middle, and we surround it with the 5 fluorines. Again, it doesn't matter how you arrange it. I'm just going to put it like this. And then we start putting our bonding pairs. 1, 2, 3, 4, 5. All right? Then 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. All right? And then we have one more pair, so that pair will go on the bromine. So I'm going to put it right here. All right? And that would be the Lewis structure. Of course, you have to calculate the formal charges. In fact, let me do that. Formal charge of fluorine. Let's do that first. And that would be 7, group number, minus half of 2, minus 6, and that will equal to 0. And then in the case of the formal charge of bromine, that would be 7 minus half of 2, 4, 6, 8, 10, half of 10, minus 2 non-bonding pairs. So that's 7 minus 5 minus 2, so that will be 0. So therefore, the charge on all the atoms will be 0, so therefore, this will be a neutral molecule. And you'll notice in this answer here, the bromine has more than 8 electrons on its outer shell. In fact, the bromine here will have 2, 4, 6, 8, 10, 12 electrons on its outer shell. And that's because bromine is located, if I'm not mistaken, bromine is located in period 5, I think it is, or 4, I don't remember exactly, but definitely below period 2, all right? So bromine can have more than 8 electrons on its outer shell. Okay, so that's in the case of the first example. In the case of the second example, sulfate ion. So let's see how that is done. So let me go here, clean this up. So in the case of sulfate, SO4 2 minus, all right? So we do like we did before. Sulfur will contribute 6, oxygen will contribute 6 each, multiplied by 4, that's 24 electrons. And then we have the negative charge. There are 2 of them, so we have to add 2 electrons. So this gives you 32 electrons, which is equal to 16 pairs. We put the sulfur in the middle, surrounded with the oxygens, and then we put the bonding pairs. 1, 2, 3, 4, then non-bonding pairs around the terminal atoms. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Then we calculate the formal charges. In the case of oxygen, that would be 6 minus half of 2 minus 6 equals minus 1. And in the case of sulfur, that would be 6 minus half of 2, 4, 6, 8 minus 0. And that would be 6 minus 4, that would be plus 2. So each oxygen has a minus 1 charge. And the sulfur here will have a plus 2 charge, all right? So the next step, you'll notice that we have 4 negative charges. I'm sorry, I made a mistake. This should be plus 2. This should be plus 2. All right, so here we have a situation where we have 4 oxygen atoms, each carrying a negative charge, bonded directly to the sulfur atom, which has a plus 2 charge. So if you remember what we did in a situation like this pair of electrons will come down here, this pair of electrons will come down here, and you're going to end up with S, double bond O, single bond O, minus, single bond O, minus, single bond O, minus. And that would be, oh, I'm sorry, another mistake I made. That negative side will go. This pair of electrons will become a shared pair of electrons. So you're going to have a double bond here. All right? And this will be the final Lewis structure for the sulfate ion. And again, you'll notice that the sulfur here will have more than 8 electrons on its outer shell. 2, 4, 6, 8, 10, 12 electrons on its outer shell. And sulfur, if I'm not mistaken, is in period 3. So therefore, that is allowed for sulfur. So this will be the final answer for the sulfate ion. Okay, so the next one, the next example is the sulfur trioxide molecule. So let me do this one here. SO3. So go through the steps like before. Sulfur will contribute 6 electrons. Oxygen will contribute 6, but we have to multiply that by 3. So that's 18. So that gives you 24 electrons, which is equal to 12 pairs. All right? Then we put the sulfur in the middle, surround it with the oxygens, and then we put the bonding pairs, 1, 2, 3. Then the non-bonding pairs around the terminal atoms, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then we calculate the formal charges. In the case of oxygen, that would be 6 minus half of 2 minus 6 equals minus 1. And then in the case of sulfur, that would be 6 minus, hold on, let me see here. Half of 6 minus 0, which would be equal to plus 3. So each oxygen has a minus 1 charge. The sulfur has a plus 3 charge. So in this case, the 3 negative charges will cancel out the 3 plus charges by the movement of the electron pairs as shown. and this would be the final answer. Right here. All right. So that's how that one is done. Okay, and then let's see here. The phosphate ion. That's the final one in this list of structures that we need to determine. So the phosphate is PO4 3 minus. So again, we do the valence electron count. Phosphorus will contribute 5, oxygen will contribute 6, multiplied by 4, so that's 24. And then the negative charge here would be plus 3. So this gives a grand total of 32 electrons, which is equal to 16 pairs. We put the phosphorus in the middle, surround it with the 4 oxygens. Then we put the bonding pairs, 1, 2, 3, 4. Then the non-bonding pairs, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Whoops. Okay, what's going on here? Okay, my pen is not working. Okay, I'm not sure what's going on. Okay, I'm not sure what's going on here, but basically, you're going to have, you know, let me quickly go to my PowerPoint here and do it on this. I'm sorry about that, folks. This just happened. So in the case of, what in the world is going on with my pen? Okay. Okay, I'm going to stop here and try to solve this problem and work on this last one. All right. So after that, then we're going to talk about resonance. Okay, so until next time.